I've got a big head. Okay, so we're going to talk 11 and 13. So, uh, let's see. So with 11, by the way, always think before you dive into substitution, consider power rule, or is it something you just straight up recognize? And that should hopefully be a fleeting thought, not something you're going to spend a whole lot of time thinking about. It's not a power rule. That's a weird product. And I see a chain rule thing to it, and I don't recognize it. So we very quickly eliminate those, and we're down to U substitution. What would you choose for your U? Now, generally, with U substitution, you're looking for things that are like inside something else, stuff inside parentheses, under a square root, in the denominator. Sometimes there's not parentheses around it, but a lot of times you choose your denominator as a U. Things that are inside an exponential. So I'm kind of going off on an aside here, but on 32, if I'm going to do U substitution, I'm going to choose the cosine because that's inside the E function. Right? So that's where those are the places that I generally look for a potential U. Same thing on 67. I see an ugly exponent. I'm going to let that be my U first. Did we do that one yesterday? We did one similar to it. Anyway, so that's kind of what I'm thinking. There are some exceptions to that, but that's where I start. Whoops, not where I want to go. So here I am going to let U be the 1 minus x squared. And then I'm going to see if that works. When you find the du, a mistake I saw some of y'all make on the warm-up yesterday, I believe it was, and I was expecting a lot of mistakes because we have not done anything as a class with U substitution as of yesterday morning. When you find du, you are simply finding the derivative of whatever you chose for u. So we're going back to what we've been doing for months. What is the derivative of 1 minus x squared? It's negative 2x. All you're doing is the derivative of what you chose for u. Don't look at the problem and try to find du in the problem. We'll do that later. But your first step is simply to differentiate your choice for u. I do move the dx over here. The mistake some people were making is instead of doing the derivative of this, y'all were looking up here and saying, well, if this is my u, then I guess x dx is my du. And you were trying to find your du in the problem initially. Well, x is not the derivative of 1 minus x squared. So please don't do that. You're simply differentiating whatever it is you chose for u. Then we hope to find this in the original problem. And if you can't make it happen, then you have to start over and choose something different for u. Okay? Can I make negative 2x dx happen? Yes. If all you're missing is a number, I can put that negative there. I need to offset it with the reciprocal out here. So I put a negative 2 on the inside. I put a negative 1/2 on the outside. Now we're ready to substitute. The negative 1/2 stays there. Common mistake is to forget about it. Negative 1/2 stays there. The negative 2x dx, I start by replacing those. That's why we call this substitution. You're literally taking things out that are equal to each other and replacing them. So negative 2x dx is equal to du. So that becomes my du. Please put the du off to the side. Do not put the du here. And then the square root of u. There's my u. Don't do that. That's wrong. What's wrong with that? The du ends the antiderivative right there. As you have it written, you're not taking the antiderivative of square root of u. You're taking the antiderivative of 1. So please, please, please remember that the du does go at the end of the integral. And so this substitution would end up being the square root of u du. And then we ignore the original problem and we have a whole new problem to solve. The square root of u is u to the 1/2. And so that's u to the 1/2. We'll add 1 to that. That'd be u to the 3/2. We'll divide by 3/2, which is the same as multiplying by 2/3. Don't forget the negative 1/2 stays out here. And then we substitute the u back in. And I'm going to go crazy. I can cancel these 2's while I'm at it. And that will leave me with negative 1 minus x squared to the 3/2 over 3 plus a c. How does that make you feel? Good? Good. All right. For 13, what would your u be? U would be 1 minus 2x. What's the derivative of 1 minus 2x? What? Negative 2, right? Negative 2 dx. And so I would put a negative 2 up here somewhere. I'm going to squeeze it right here next to the dx. So negative 2. And I'll put a negative 1/2 here. And when I substitute, the negative 1/2 out there stays. Always take care of the du first. Negative 2x dx comes out and it gets replaced with du. 1 minus 2x is my u. It's all to the 9th power. If you want to put that in parentheses, you can. Doesn't matter. Then we would integrate it. Antiderivative of u to the 9th is u to the 10th over 10. The negative 1/2 stays here. And then I would replace the u with whatever u was. So it's negative 1/2 times 1 minus 2x to the 10th over 10 plus c. Are we okay? Okay. The colors that I used on number 13. If I were doing this problem, the only thing I would have written on paper is what's in blue. I probably would have done this. I probably would have maybe underlined this and written u and then du. I may have done that. But for straightforward, clean substitutions like this, a lot of times I skip the formal u steps. If you can visualize it in your head and then do the antiderivative, you can skip a lot of works. And that's going back to Tyler's question. If you can do it in your head, that's fine. I think it's a good idea to at least write down, if you need to make an adjustment, like throwing in the negative 2, I think it's a good idea to actually put that and the negative 1/2 there to have a visual. I think doing it completely in your head is a little bit dangerous. But I would like for you to try to get to the point where you're comfortable skipping some of the steps. And if you're not comfortable skipping steps, then don't skip any. It's kind of dumb to skip steps if you know you're going to increase your chances of missing it significantly. Good. You want me to leave you alone and give you a minute to try some more? Are we understanding the mechanism of u sub? Just remember, the actual substitution is an algebra step. You are simply taking out and replacing things that are equal to each other. And that is fine. Have I done a problem like 22 in any of the lessons? Because 22 is an interesting problem. What would you choose for u? Huh? I hear root x. Did I hear something else? I'm waiting for a very specific wrong thing because somebody always suggests this. At some point, somebody's going to suggest this. X. Did anybody do u equals x? Okay. I'm going to show you what happens because some people might at some point in your life consider the substitution u equals x. If you do u equals x, what is the derivative of x? It'll be 1 dx. And as long as you can account for the du, then you can proceed with the substitution. Do I see a dx in the problem? Yes, it's right here. So I am allowed to now go on with my substitution. I take out the dx, I replace it with the du. Then I have to get rid of every other x. So instead of sine of square root of x, I'm going to have the sine of the square root of u. Instead of square root of x, I'm going to have the square root of u. How does that help me? It doesn't, unless you just have a fear of the letter x, right? You never, ever, ever do the substitution u equals x because it will spit out the exact same function you had just with a different variable. It does not change the problem at all. So never do u equals x. It must be, even something simple as u equals x plus 1 might be enough to alter the problem to something that you can do. But you never, ever do u equals x. We will do u equals square root of x. Now I'm curious, which square root of x are you looking at? Okay, it actually is the one inside the sign because that square root of x is inside a sign. However, I did tell you that you very frequently choose u from the denominator. So if you chose u as square root of x because you see square root of x in the denominator, that was the wrong place to look. But as long as you follow the rules of substitution, you are still going to end up with the right answer. What is the derivative of the square root of x? It is 1 over 2 root x times dx. All year, I have been telling you that I want you to get to where you are doing the derivative of root x as 1 over 2 root x, because a day is coming where if you can recognize that derivative, it is tremendously helpful, and this is the day. It is here. It has arrived. Because in u substitution, you will almost never see x to the negative 1/2. It will always be presented as something over square root of x. So please, if you are not there yet, now is when you need to have this in your mind. And before I do anything, I have to account for this du. Is there a 1 over 2 root x in the problem? Almost. I have the root x in the denominator. I have the dx. All I'm missing is a 2 with that. Yes? Now, I've also said make sure you substitute the du first. You have to do that first, because if you substitute the u first, you might be tempted to turn this into sine of u over u. But the problem is that did not account for the dx, right? So you do not substitute the u first. You always substitute the du first. Then we go back and see if u goes anywhere. And so I need to put a 2 in the denominator. If I put a 2 in the denominator, I need to put a 2 out here, because really I put a 1/2 in here. Now I'll substitute, and once you substitute, this turns into a nice problem. The 2 on the outside stays. 1 over 2 root x dx is my du. Sine of root x becomes sine of u. And what is the antiderivative of sine? Negative cosine. So we're going to have negative. The 2 on the outside stays. Cosine of u, and u is square root of x. I'm just going to go ahead and replace the u with square root of x here. And there's our answer. Are we good? Are we good? All right. This type of derivative, this type of u du substitution, notice that my u is not a fraction, but the derivative of u was. Okay, I call that a hidden du, because the du is really a fraction. It's kind of hiding there under the, I don't know, my teacher friend in Mountain Brook calls it a hidden mistress that's hiding under the bed. But the derivative is really a full fraction. If you need to rewrite it, you can rewrite the problem as sine square root of x times 1 over root x, if it makes it a little bit easier to see the fraction-y part of it. But be aware of functions that are not fractions, but give you fractions as a derivative. Can you think of any other functions that are not fractions but have a fraction derivative? Natural log x is one of them, and all of your inverse trigs. Those are the main culprits that will give you that hidden du situation. So think about that when you run into problems and you see those functions. Square root of x is obviously one of them. We just did that. So if you see a square root of x, a natural log x, or an inverse trig, it's very possible that that stuff in the denominator is actually serving as the du and not the u. And 25 is one of those. And 25 is one that I told you I could look at, and I consider this one to be one of the easiest ones. The reason I consider this one of the easiest ones is because if I let u equal the natural log of x, 1 over x, the 1 over x along with the dx, all of that is my du. And so in my head, I'm seeing u squared. What's the antiderivative of u squared? U cubed over 3, and my u is natural log x. We didn't even have to make an adjustment. We didn't need to throw any constants in there. That one was ready to go. That's why I consider 25 one of the easiest ones. But y'all have this innate fear of logs, and you're going to make it hard because logs they're a pain, I guess. I don't know. I like them. They're fun. They build character. What rolls downstairs, a loner in pairs, rolls over the neighbor's dog. Y'all don't know the log song? What's great for a snack and fits on your back, it's log, log, log. It's from Ren and Stimpy, an old 80s, 90s cartoon. Yeah. They're making fun of Slinkies, by the way. That was actually the Slinky song, but they had a log, and it was a toy that you just like carried around as just a log. Good old Ren and Stimpy. Let's see, what else do we have? How much time do we have left? Never enough! Shall I leave you alone and let y'all keep working? I'm going to do that. I wanted to talk to you about the whole hidden du thing, because that does show up a few times. And as you work through the problems, they will get more and more difficult. Probably starting with 45. Okay, so here's my 32. I skipped a lot of steps on both of these. 35 was almost identical to 25. I'll talk about 32 in a second, but 35, the derivative of arctangent x is 1 over x squared plus 1 dx. So the amount of work that I have written there is usually what I do if I'm doing these on my own. If you need to do the formal substitution and write the actual antiderivative in terms of u, then do that. But just for efficiency reasons, if you can get to where you can skip some steps, it gives you more time to think about the harder problems. 32, the derivative of cosine is negative sine. So you can see I stuck a negative 1 in front of the sine. And then I had to put a negative 1 on the outside. And the part that's going on in my head, this part was in my head for number 32. I had a negative on the outside, and that turns into e to the u cosine, du. That's what I was seeing in my head. And the antiderivative of e to the u is e to the u. So I just replaced the u with a cosine t. And the negative on the outside comes along for the ride. How are these? Are they clicking a little bit? Cool. Let's talk about 45. Did anybody figure out 45? Sure. All right, hang on a sec. We're good. Some teachers like to teach you like some memorization antiderivatives, and sometimes that's good. Like sometimes the way you work it out by hand is really cumbersome, so memorizing certain things may be beneficial. This is not one of them that I memorize. What is the trick to this one? Split it up. Okay, cotangent is cosine over sine. And if I ever am doing the antiderivative of a fraction, I will always look first to see if the top is the derivative of the bottom, because if the top is the derivative of the bottom, then I recognize that as your derivative template for a natural log. So the antiderivative is natural log of the bottom, right? That's one of my favorite antiderivatives. They're the easiest ones to me because it's almost recognition. And at this point, I see that cosine is the derivative of sine. I'm not going to do any u work at all. I know that that's going to end up being the natural log of sine x. Don't forget the absolute values. Good? What about 49? Have we had a chance on that one? It's not a natural log yet. There will be a natural log in the answer, but that's not all it is. I would check that. What is the derivative of 1 plus x squared? It's 2x. I've got a 1 plus up there. And that's why I can multiply the entire top by 2. That will give me a 2x, but it also gives me a 2 plus, which is not the exact derivative of the bottom. So it's not a natural log. That's why I like to think about that. It's a very quick thought. You're not going to spend a whole lot of time pondering that, but that fails. So guess what we'll do? Any ideas? Any ideas? Huh? STDs. STDs. Now, you may be looking at that denominator and saying, that's not a single term. That is two terms. It is a 1 and an x squared. Technically, that's true. However, as long as you are adding in the fraction, or I'm sorry, if you are adding or subtracting in the numerator, anything can be an STD as long as you keep the entire denominator in one piece. So I'm going to split this into 1 over 1 plus x squared and then x over 1 plus x squared. And when I do that, it turns it into two very, very nice antiderivatives. I'm going to separate it into two like this. If you want to write 1 plus x over x or whatever, if you want to write it inside one integral, you can. However, I'm going to completely separate it like so. And both of those, one of them should definitely be insultingly easy. Which one is insultingly easy? The first one. Why? Because that you should recognize as the derivative of inverse tangent x. There is no process for that. The process for solving that is to learn your inverse trig derivatives, like I asked you to about 6 months ago. I think. Didn't I call all of y'all like in May and tell you to learn your inverse trig derivatives? I think I did. All right. Okay, so inverse tangent of x. And then what about this one? Dude, this one will be a natural log. Is the top the derivative of the bottom? Not yet, but I can easily make it happen. I can put a 2 and a 1/2. And so the antiderivative of that one will be 1/2. Natural log of 1 plus x squared. For this particular problem, the absolute values are not necessary because 1 plus x squared is always positive anyway, but it's never wrong to put them. So I just always put absolute values. You could, if you want to, put two constants, one constant for inverse tangent of x and one constant for this one, which I guess I should put a different one. But that is the same as just having one constant in the end. So if I do a whole bunch of antiderivatives, I'll just put one c at the end to represent all of them. How's life? Yeah? Aren't these fun? They're like little puzzles. I think I want to jump to 74 and 80. How much time do we have? 8 minutes? Let's do 74 first. I am recording, right? Yes, I am. My microphone's on, right? Yes, it is. I accidentally turned my microphone off halfway through second period, so half of theirs is silent. Okay? So this is a definite integral. That means you don't need a plus c, and when we are done, we will need to substitute 1 and 2 to evaluate the integral. But we don't let the 1 and 2 interfere with the antiderivatives. As a matter of fact, we ignore those completely for the majority of the work. We only come back to those at the end. So, what do you want to do? Huh? U equals, okay, x minus 1 is the only viable choice for u. I guess you could do x if you want to make it weird. So u is x minus 1. Then I need to find the derivative of x minus 1, which is 1 dx. The dx is part of it. The dx is part of the u, of the du. So please write that. Please write that. Do I see a dx? Yes, that means I can proceed with my substitution. So I start by taking out the dx and I put a du in its place. Then I look at everything else. And I have to get rid of every other x. X minus 1 is u, so that becomes the square root of u. All right? But we still have 1x left over that must be accounted for. And that's going to be u plus 1. And this was in one of the videos, the second one that you're supposed to watch. And remember that substitution is in the world of algebra. The actual substitution step is not calculus. We're just taking things out that are equal to each other. And so as long as you are inside the world of algebra, you can substitute however you want. And I can, with algebra, turn x into u plus 1 by adding 1 to both sides. And then I replace that x with u plus 1. And I have now successfully substituted everything. Good. Can you do that antiderivative? It can be done now. We have to do a little bit of work because it's a product, and at some point in your life, you will learn how to do the product rule in reverse, and you could do that technique with this problem if you wanted, but it's a pain. The easier option is that I can now distribute my square root of u. I could not distribute originally, or at least not easily. You can take that x and move it up under the square root, but it's not going to help you any. But now I can distribute, and it'll turn this into a power rule. Just remember, you add the exponents. So that'll be the antiderivative of 1 plus 1/2 u to the 3/2 plus 1 times square root of u is u to the 1/2. And I like to see the actual exponents because it makes it easier to add. The antiderivative of u to the 3/2 is 3/2 plus 1 is 5/2. And if you divide by 5/2, you multiply by 2/5. Plus 1/2 plus 1 is 3/2. And multiply by 2/3. And at this point, we have two options. One is to plug x minus 1 back in for the u. The other option is to think about the fact that this was a definite integral, and I prefer to do this. There are some problems, and one of them was in the video. There are some problems where you have to use this technique. I'm going to convert my limits of integration. If x is equal to 1, then u is equal to x minus 1, which is 0. And so for my integral in terms of u, my lower limit is 0. And if x is equal to 2, then u, which is equal to x minus 1, will be 2 minus 1 is 1. And now I can finish the problem and never go back to x's. This one's really nice. Plug in 1, that'll be 2/5 plus 2/3. Plug in 0, and you get 0 plus 0, and I would stop there. You could get a common denominator if you want. It actually wouldn't be too bad, would it be? 16/5? 16/15, I mean. How do we feel? Questions, comments, concerns? Shiny, happy people? I want to take this up, but I so desperately want to go over number 80 first. 80 has got a very, very, very weird approach that you have to use. It is U substitution. 84 gives you a huge chance, so hold on to it. I don't want you to do those two tonight. I'm going to put something else up for y'all to look at tonight. But just hold on to this and remind me tomorrow to take this from you so you can get some points for it. And we do get out at 40, right? So we have like 3 minutes. That's not enough time to do either one of those two problems. So we're good? Okay. Oh, I'll see y'all Thursday. I don't see you tomorrow.